Math 2414, volumes. Volume of a solid of revolution, rotating around other axes, example 2. For the third time in this series of videos, we're revisiting this lamina again. The one bounded above by y equals 3x, or on the left from that perspective, and bounded below by y equals x squared, or bounded on the right from that perspective. We've already found the intersection points. There were the origin, and there were also the points 3, 9. But this time we're going to find the volume by rotating this lamina around the axis x equals 4, way over here to the right. Again, I can't stress enough that the trick to these is to set up a picture, identify what you're looking for, and connect it to what you know. Since I'm rotating around a vertical axis, x equals 4, I want to think about the cross-section being perpendicular to the axis of rotation. So we're going to cut this across here at some y value. So we're going to go y, cut that, spin it around, and when I show you the cross-section, it's going to make a washer. Just a reminder, when you have a washer with an outer radius capital R and a little radius inner r, then let's draw it this way. When you have a washer with a capital, an outer radius of capital R and an inner radius of lowercase r, then the area of that washer is pi capital R squared minus pi little r squared. Literally one circle minus another. Let's embed the capital radius, the outer radius and the inner radius in this picture. The outer radius is simply the distance from the axis of rotation to the outer portion of the lamina. Our outer radius is here. The inner radius is the distance from the axis of rotation to the innermost part of the lamina. The inner radius is here. We know we're going to do dy because we made a y cut, and so we're going to be going from 0 to 9. So we need to find both of these radii as functions of y. Let's start with the upper radius. The upper radius does not touch the x or the y-axis, which means this distance cannot be a coordinate of a point. But when that happens, you complete whatever displacement it is to an axis. Since this is a horizontal displacement, let's complete it over to the y-axis. And since this is a distance from the y-axis, we'll just call it x. That's what x measures. How far do you go from the y-axis? And what do we know about x and capital R? Together, they stretch all the way from the y-axis to the axis of rotation, which is a distance of 4. So we know that x plus that that outer radius has to equal 4, which immediately implies that the outer radius is 4 minus x. But remember, we're going to do a dy integral. We need the radius as a function of y. Right now it's a function of x. So now I got to figure out what's the relationship between x and y right here. On this word pair, we'll call it x comma y, because according to this picture, that's what we should call it. It's over x and up y. That ordered pair is on this boundary, whose equation is y equals 3x. So we know that up here in this picture, we have y equal to 3x. We need to know what x equals so we can replace this. This implies that x is equal to y over 3, which means that our capital R is 4 minus y over 3. So there's the outer radius as a function of y. For the inner radius, we play the same game, just on a different graph. And I hate using x again, but I'm about to. Our inner radius is representing this distance, but that is not a displacement from the y-axis. The y-axis is all the way over here. So we complete the picture by asking ourselves, where is the displacement from the y-axis from this point? And it's here. being a horizontal displacement, we're going to call it an x again. And be careful, that's a different x than up here, and I'm feeling bad about that. Maybe I should subscript these x's with capital R and little r just to distinguish between them. It's not crucial, but I hate using the same letter in two different capacities. So we know that this x subscripted with little r plus our inner radius r is the total displacement from the y-axis to the axis of rotation. That's just a distance of 4. So this implies that the little radius is 4 minus our x little r. But what do we know about this point? This point we'll call, well, if we're going to call this x little r, we should put that in the order pair. I'm going to back up and do it in this one too. And it's up y. So that point is on the parabola. So we can say, but y is equal to x squared, and this implies that xr squared, if you will, y is equal to x sub little r squared because we're on the parabola, and that tells us that x little r is going to be the square root of y. So I can substitute that here. Now right now I can tell what some of you are feeling. You're just doing stuff at random and it's going to work. I'm not doing it at random. I'm doing it for a purpose. I'm motivated. What's motivating me? I'm rotating around a vertical axis, so we're taking a horizontal cut. So we're cutting at y. We're going to do a dy integral. I need to know the area. The area is currently a function of the outer and inner radii. But I need to know what those are in terms of y. The radii representing horizontal distances, I relate to other horizontal distances that I call x, so that I can get a relationship between them, but I need them as a function of y, so then I have to go to the graphs to establish the relationship between the x's and the y's, so that eventually I get the radii as functions of y's. Now, is it big? Is it messy? Yeah, it kind of is. But I've got everything that I need. Our volume is going to be the integral from the bottom to the top. Remember, we're doing y's, 0 to 9, of pi times capital R squared. So pi times capital R, but capital R was 4 minus y over 3 squared, minus pi times little r squared, but little r is equal to 4 minus the square root of y, dy. It's going to be a little bit of a mess, but it's just algebra. Let's pull out the pi, 0 to 9. If I write this out twice and multiply it, I'll get 16 minus 8y over 3, or 8/3 y, plus y squared over 9, minus, and I gotta be careful because this minus is going to distribute across the results of this. Let's figure out this first. If I square this binomial, I'll get 4 times 4 is 16. I'll get twice this product, which is negative 8 squared of y, and then plus the square of this plus y. All that's being subtracted. Remember, I pulled out the pi. Let's see. Well, the nice thing is the 16s cancel, so those are gone. I got some y terms here I should combine. Negative 8/3 y minus 1y. Well, that's negative 8/3 minus 3/3, which is negative 11/3. Haven't integrated yet. So negative 11/3 y. This is the only y squared term, so plus 1/9 y squared. I know I just changed the format. Y squared over 9, 1/9 y squared, tomato, tomato. And the only term I haven't accounted for is this guy. Minus minus is plus 8 y to the 1/2 power in anticipation of taking the antiderivative. The good news is the lower limit is 0. I'm looking for a ray of sunshine here. If we integrate this, let's take it over here. The integral of negative 11/3 y is negative 11/6 y squared. Hopefully I don't have to elaborate on that calculus 1 move. The integral of plus 1/9 y squared is plus 1/27 y cubed, or rather I should say the antiderivative. And the antiderivative of plus 8 y to the 1/2 is plus, let's see, y goes to the 3/2, multiply by 2/3 and get 16/3. From 0 to 9. And let's clean this up real fast. 0 annihilates it, so as a lower limit it's gone. When I put in the 9, I get 9 squared is 81. But 81 will reduce by 3 here, so we'll get a 2 on the bottom. 81 divided by 3 is 27, but then we have times 11, which is 297. That should be negative 297 halves when I put the 9 here. Plus, 9 cubed is 729, and 1/27 of that is 27. Plus, here's a 3/2 power. Square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9. And 9 times 16 is 144. And now we just have to put it all together. It's all going to be halves. Let's go ahead and combine the whole numbers. 27 and 144 is 171. So this is plus 171. Well, let's make it halves by doubling it. If I double 171, I get 342. And then 342 minus 297 is going to be 45. So we get 45 pi over 2. You know, I say the setup is the hardest part, but you may disagree. The point that I'm making in all of these is, to find the volume of a solid of revolution, it's going to be a disk or a washer. So one radius or two. Figure out where the radii are in the picture. Connect them to x and y somehow. If it's on the x or y axis, you're lucky you have an ordered pair, one of whose coordinates is r or little r. Big R or little r. If your radii do not touch the x or the y axis, then complete the distance so that it does. Establish some additive relationship like we do here. And it should always be a constant because you're measuring to the axis of rotation, which will always be parallel to the x-axis or y-axis in this class. But then you also have to get it in the correct variable, and that's where the equations come into play. This takes practice. I'm not going to lie to you. The first time I learned this, when I took calculus my senior year in high school, there were problems with these that I totally struggled with, and I expect you to struggle with some of them. The way you get better at doing them is you try them. You don't copy from Slater. You don't go to Wolfram and try to type the question so that it can answer it for you, and you don't just copy an answer. You try them. If you get stuck, contact me. If you're watching this and you're currently in my class, you have my cell phone number, text me. I want to help you, but I can't help you if you don't ask me for the help. All right, that was fun in a sick sorted way.